Hello guys, welcome to this session. So in this session guys, we will talk about hyperparameters. So first we will discuss about what are hyperparameters. Hyperparameters are different parameter values that are used to control the learning process and have a significant effect on the performance of machine learning models. So before training a model, we have to set the values of the hyperparameters. Whenever we start a model training, we have to pass some values to the hyperparameters, or we can use them with their default values. But every time default values will not work on every other data set. So sometimes we have to perform hyperparameter tuning so that we can get the best value of the hyperparameters. An example of hyperparameter in the k-nearest neighbor algorithm is the number of nearest neighbor. So this is a hyperparameter. Distance metric, this is also a hyperparameter. So these parameters are tunable and can directly affect how well a model trains. So whenever we perform hyperparameter tuning, we get best hyperparameters. Right? And the best hyperparameter we can use for the model inference, or we can say for the making prediction. If we talk about difference between parameters and hyperparameters, so parameters are required for making predictions, and hyperparameters are required for estimating the model parameters. Means if we want to get the best value of the parameters, right? So we have to choose the right value of the hyperparameters before training a model. They are estimated by optimization algorithms like gradient descent, ADAM, or ADAGRAD, and many others. So parameters, so the values of the parameters like coefficient or intercept, right? So the values of the parameters we can find with the help of some optimization algorithms. But in the case of hyperparameters, they are estimated by hyperparameter tuning. So in scikit-learn, we have some inbuilt classes, right, to perform hyperparameter tuning. In the case of parameters, they are not set manually. We cannot set the values of the parameter manually. But in the case of hyperparameter, we can set the values manually to the hyperparameters. Then the final parameters found after training will decide how model will perform on unseen data. So after a model training, we will get the values of the parameters. And in the case of hyperparameters, the choice of the hyperparameter decide how efficient model training is. In gradient descent, the learning rate decide how efficient and accurate the optimization process is in estimating the learning rate. Is basically a step size, right? Or we can say it, we can say how quickly we want to reach toward the minimum point of a loss function. Whenever we build a neural network, right, we have to find the right value of the learning rate. Hyperparameters we have to tune before a model training, right? And the values of the parameters we always get after a model training. Here you can see the best hyperparameters we can get after hyperparameter training. And while training, we can pass these best hyperparameters so that we can get the best value of the model parameters. Next, we have what is hyperparameter optimization. Hyperparameter optimization is the process of finding the right combination of hyperparameter values to achieve maximum performance on the data. For example, if we implement KNN, right, on a data set, so we have to find the right value of the n neighbors, right? N neighbors is an hyperparameter of KNN algorithm. So if you want to get high performance of the model on the on-scene data, we have to pass the right value, or we can say optimal value of the hyperparameter. This process plays a vital role in the prediction accuracy of machine learning algorithm. Most of the machine learning algorithms come with default values of their hyperparameters. Okay, I'll show you in the definition of KNN. So KNN, scikit-learn. So here you can see these are the hyperparameters with the default values. But every time these default values will not work on every data set. Right? So sometimes we have to change these values. If we talk about n neighbors, so the default value is 5. If we talk about weights, so the default value is uniform. And here we have the default distance formula is Minkowski. Right? So these are the hyperparameters. But if we talk about regression, logistic regression. So after modeling a logistic regression, we will also get a parameters. So first, these are the hyperparameters. And if we talk about parameters, so after model training, okay, so after model training, we will get the coefficient. So coefficient and intercept, these are the parameters. Right? These are the parameters. Right? So we cannot set values of these parameters manually. Right? So after model training, we will get the values. So most of the machine learning algorithms come with the default values of the hyperparameters, but the default values do not always perform well on the different type of machine learning projects. So this is why we need to optimize them in order to get the right combination that will give us the best performance. A good choice of hyperparameters can really make an algorithm shine. So if we pass the right value to the hyperparameters, right, so we will get an effective model that will perform well on the unseen data. Okay, now there are some strategies that we can use for hyperparameter tuning. So first is grid search. This method tries every possible combination of each set of hyperparameters. Okay, I'll show you about this grid search in scikit-learn. So grid search is a technique of scikit-learn, and we can search about grid search. So there is an inbuilt class that is grid search CV. So this class we can use for hyperparameter tuning. So this technique tries all the possible combination of the hyperparameter values. So here we can pass estimator object, parameter grid means a dictionary where we can pass the list of possible values of the hyperparameters, then scoring method. Okay, and rest of the hyperparameters we can leave with the default values. This is how we can import grid search CV from sklearn.model selection import grid search CV. Suppose if we load a iris dataset and we have a model here SVC. In the further classes, we will discuss about what is SVC model. But if we take an example of KNN, so in the case of KNN, we can pass here n neighbors. We can pass n neighbors as the key, and corresponding to this key, we can pass a list of possible values. Right? After that, this grid search CV will try every possible combination, right, while calling the spec method. After this here, we can find the best score, best parameters. So this usually uses more computation power and it takes a long time to run since this method needs to try every combination in the grid size. And so this technique consumes more computational power. This approach is called grid search because it searches for the best set of hyperparameters from a grid of hyperparameters values. And the drawback is grid search CV will go through all the combination of hyperparameters, which make grid search computationally very expensive. So if we pass lot of possible values of an hyperparameter, right, then it will take more time to find the best combination. So we can say this is a drawback of this technique. Another technique we have random search. But in scikit-learn, there is a class that is randomized search CV that solves the drawback of grid search CV as it goes through only a fixed number of hyperparameter setting, and it moves within a grid in a random fashion. It means it will randomly apply the combination to on the data, and this approach reduces unnecessary computation. So this chooses the hyperparameter sample combination randomly from the grid space, right? Or we can say, or from the hyperparameter values that we will provide in the form of dictionary. But this search can be extremely effective in practice as computational time is very less. Okay, so let's implement git CV and randomize search using scikit-learn. Okay, so this hyperparameter tuning. Hyperparameter tuning we can also perform using SageMaker, right? That we will discuss uh, later in the session. So I'm going to import some necessary libraries here or classes from sklearn dot dataset. Okay, so here I'm going to take load iris dataset just to understand the process of hyperparameter tuning. Just to understand the process of hyperparameter tuning, I'm going to take this iris dataset from sklearn dot model selection, import grid search CV, and the model that we will use, that is KNN. So from sklearn dot neighbors, import k neighbor classifier. Next, we can import from sklearn dot model selection, import train task split. Next, we can import from sklearn dot matrices, import accuracy score. Okay, next iris equal to, then x equal to iris dot data, y equal to iris dot target. Okay, next we will split the data into train and test. Train test split, we can pass x comma y comma test size equal to 0.25, and here we can take variables like x train, x test, y train comma y test. Next, so we will initialize the model. So KNN, or we can say model equal to k neighbor classifier. Next, we will create an object of class grid_cv. Here, first argument will pass here model object, that is a model, comma. Okay, and before this, we have to create a dictionary where we can pass a list of possible values of the hyperparameter that we want to tune. So let's take a parameter dictionary equal to, so key we can take the parameter that hyperparameter that we want to tune. So we want to tune, you can see in this key neighbor classifier, we want to tune this hyperparameter. You can also tune others, but in this example, I'm going to tune only this hyperparameter and neighbors. So always set the hyperparameter as a key, and we can pass a list of possible values. Like we want to tune on 2, 3, 4, 5, 6, 7. Or you can also pass a range, right? You can also pass a range here, like 2, 7. So if you want to tune some others, so you can create more pairs in the same dictionary. And now here we can pass parameter grid equal to para dictionary. Then we will pass scoring method. So this is a classification problem. Here we will pass scoring method accuracy, and the object, let's take a grid equal to grid_cv. Next we will grid dot fit, we will call fit method here, and we will pass here x train comma y train. Here we are getting some warning, so if you want to ignore the warning, so there is a way, that is we have to import warning, and here we can write warnings dot code to ignore the Python warning. Ignore warnings Python. Depreciate warning, or Okay, we can import, we can copy this line. So warnings dot filter warning, ignore, and category is future warning. So if we get any future warning, that will not be displayed in the Jupyter notebook. Right? So we want to ignore such kind of warnings. So warnings dot filter warnings, ignore, category equal to future warning. But if you get any warning like depreciation warning, right, then you will get the message. But if there is any future warning, so in that case, the message of that future warning will not be displayed in the Jupyter notebook. And if you run this again, if you run this line again, you can see now we are here, we are not getting any warning. Okay, next here we can find some other important information like grid dot best parameters. So we want to know the best value of n neighbors, and this class selected this 5 on the basis of score, on the basis of accuracy score. So grid dot best score. So best score we are getting 0.94 if we pass n neighbors equal to 5. And if you want to get the best model, so we can write grid dot best best estimator, and then we can store somewhere into a Python variable. So we can write model or tune model. We can store it into a tune model. Now this tune model we can use on the test data. Right? So there is no need to retrain this model on the same data. Right? Now this model we can directly use for the unseen data or for future data. So tune model dot predict, and we can pass x data, right, or whatever test data or future data or unseen data we have. We will get the predictions here that we can store into a variable. And next here we want to get the accuracy on the test data. So we will pass here y test comma grid. You can see now accuracy we are getting around this value, right, 0.97. Okay. So this is a process of implementing hyperparameter tuning. If you want to tune some other hyperparameter like metric, we want to tune a metric hyperparameter. This one default value is Minkowski, but we want to tune this. Or there is instead of this, let's tune weight equal to uniform. Okay, and let's see what does mean by weights equal to uniform. Here you can just scroll down and you will get the definition. Okay, so if you pass weight equal to uniform means all the points in each neighborhood are weighted equally, right? All the points in the each neighborhood are weighted equally. If you pass distance, weights equal distance, in that case, weight points by the reverse of the distance. So in this case, close neighbors of query point will have greater influence than neighbors which are further away. Means the points that are close to the query point or the test point, right, that will get the high weight, right, or higher weightage. So okay, so let's tune this hyperparameter with these two values, uniform or distance. So let me just copy this. So we can take key, colon, in the list we can pass this. Now you can see we're getting neighbors and neighbors equal to 2 and weights equal to distance. And the best score is we're getting the same, there's no change. Okay, and tune model, parenting good, the same we are getting. Okay, so this is a process of implementing hyperparameter tuning. Now if we want to implement on some other, okay, so let's take here another data set in which we will have a lot of samples, a lot of features, right? Okay, so I'm going to take iris, not iris, MNIST data set from sklearn dot data sets import fetch OpenML. Okay, and let's first download this data, fetch open ML, and the dataset name we can pass here. Amnest underscore 784. This is the dataset name that we want to download. Okay, next to amnest dot data. Okay, amnest dot data. If we take for sample at index 0, and if we get maximum value is 255, and here we are implementing KNN. Now here in the case of KNN, if we have large values in the feature, right, so our KNN model will take more time while training. Right? If we have large values in the features, and then our KNN model will take more time while training. So we can do one thing, we can just rescale all the features values into a fixed range, right? Or into a small fixed range, like a -1 to 1 or 1 to 1. Sorry, -1 to 1 or 0 to 1. So -1 to 1 range we can use uh, if we um, uh, uh, if we do have feature scaling using standard scaler, and uh, and the range 0 to 1 we can use if we do here feature scaling using normalization. So I'm going to implement here feature scaling technique or class here from sklearn dot preprocessing import min max normalization. This one, min max scaler. There is also another technique that is standard scaler. But in the case of image, we always prefer to use min-max scaler. In the case of min-max scaler, all the feature values will be converted into 0 and 1. So after data splitting, we will use this class min-max scaler. std. So min-max scaler we can use as a transformer, because this is not an algorithm for making prediction. Okay, this is an algorithm to transform the data into some another form. So std, let's say scalar equal to min-max scalar. Min-max scalar. You can see the definition of this: transform features by scaling each feature to a given range, and the given range is 0, 1. Right? You can also change this range, but the default range is 0, 1. So all the features values will be converted into this range. So this is a transformer, means we can transform the data into some another form. So scalar equal to scalar train equal to scalar dot fit underscore transform. So for training data, we always use fit underscore transform, and for testing data, we always use only transform method. Scalar underscore test equal to scalar dot transform. We can pause here X test. Now we can use this model. Okay, and okay, before this we have to mention our X and Y. So X equal to amnest dot data, and Y equal to amnest dot target. Split the data, okay, X comma Y will make scalar, transform the features, initialize the model. Now here we will use only one hyperparameter, otherwise it will take more time while training. Then if you run this, we can pass model parameter get scoring method. Okay, now we will call fit method here. Here we will pass scalar train, because now all the features we have converted into this range 0 and 1. Right, so scalar train comma Y train. So we if we have large amount of data, we always prefer to implement hyperparameter tuning using SageMaker instance. using SageMaker notebook instance. But on the SageMaker, we can also use instance type that supports GPU, right? That supports GPU because if we choose an instance type that supports GPU, so our model training will be faster. But the GPU instance doesn't come with the free tier plan, right? With the free tier plan. So if you want to use GPU based instance, right, you have to pay some extra charges. Okay, here you can see GPU based instance AWS G4 instances. Okay, here you can instance for model training or for deep learning, the EC2 G4 based instances. Here you can see G4 AD instances. You can run this code, right, by your own self. So I'm going to uh, stop this cell. So we can run interrupt because we don't know how much time it will take to complete the training. So let's interrupt this cell. So this is a process, guys. So we need data, and then after we can split the data, or we can create a model instance, and then we can use this class grid search CV. We can pass here model object, parameter list, and scoring method. And then after calling fit method here, we will get the best parameters, best score, and best estimator. So now best estimator we can use for the testing data. Next we have another technique we have, that is randomized search. Randomized search CV SQL. So it will apply the combination randomly. Let's see. Randomized search on hyperparameters. You can see in contrast to grid search CV, not all the parameter values are tried out, but rather a fixed number of parameter settings is sampled from the specified distribution. And the number of parameter setting are tried is given by the n iteration. So I think there is a hyperparameter in this class, that is you can see n iteration equal to 10. So the number of randomization we can decide using this hyperparameter n iteration. Here you can see number of parameter settings that are sampled and iteration trades off runtime versus quality of the solution. How we can implement this? You can see. So C equal to means, so whatever hyperparameters we have, or we can create a dictionary that we have just created, and then we can use this class randomize search CV. We can pass model object distribution means this parameter grid and the random state. We can also pass the value of n iteration, and if you don't pass, it will use the default value 10. Okay, let's implement this randomized search. Here we can import randomized search. So instead of using all the possible combination, it will just apply combination randomly, right? And that randomization depends on the iteration. The default value is 10 for the n iteration. Okay, I'm not going to use this administrator because it will take more time. Let's use the IS data set. Move this one. X R-star data, R-star target. Then split the data. You can pass X in small. If you want to perform feature scaling, you can use min-max scaler. And we can next we can initialize the model. We can create a dictionary. And instead of this as CV, we can use a randomized search CV. So model, parameter grid, scoring. And here we will also pass random state. Otherwise, we will get the different output every time if you run this line. right? So let's set the state here 4, and also we want to set the n iteration value, let's say equal to 3. We're getting some error. Let's see what error we are getting. Okay, there is no argument like parameter grid. A random state C and jobs exploring parameter distribution. See, there is the argument that is parameter distribution. So here we have to use parameter distribution. Now you can see n neighbors is 5, best score is 0.94, estimator and exploring. Oh, here we are. Okay. I think here we have to pass scalar train, and here we can pass scalar test because we have just rescale our test it also. So scalar test. You can see now we are getting 0.97 accuracy in the test data. Right, so this is how we can use randomized search CV. So the difference between grid search CV and the randomized search CV is that in the case of grid search CV, it will implement all the possible combination. Right, so it will take more computation power. But in the case of randomized search CV, it will take random combination, right? And the random combination depends on the n iteration. This is how we can implement randomized search CV. Next, so we can also implement hyperparameter tuning on the SageMaker, right? On the AWS SageMaker. Okay, so there is a class. Okay, so first we have to set the possible values of the hyperparameter that we want to tune. So we can import here integer parameter, categorical parameter, continuous parameter, and hyperparameter tuner. So integer parameter we can use to set the range for the integer type of hyperparameter. Means in the case of KNN, we have hyperparameter K where we can pass integer values. But if we have any hyperparameter where we have to set the float values, okay, so we can use continuous. Same, we have categorical parameter for the categorical values, but mostly we use integer parameter or continuous parameter. So we can take a variable here, hyperparameter ranges K, which is here hyperparameter of this KNN algorithm. Yeah, okay, I'll show you what hyperparameters we have in SageMaker KNN. SageMaker KNN. Okay, so here you can see, here we can tune this K. So here we have to pass integer value. It required and number of nearest neighbor. Number of nearest neighbor. So integer range here, let's take 1:8. And then we can create an object of this class hyperparameter tuner. Here we can pass our model KNN, and this is the same code that we have seen in the last class. Right? In the last class we have seen this code. So set hyperparameter. Okay, here we can pass our model KNN, this one, and then we can set the objective metric name. Means for the test data or for the validation data, we want to use accuracy here. Okay, I'll show you what metric we can use in the case of KNN. Let's search here. SageMaker KNN objective matrices. Okay, so here let's see what matrices we can use. Parameter SageMaker KNN objective metric hyperparameter tuning parameter tuner. Okay, here you can see test accuracy and test MSE. So in the case of regression, we can use test MSE, mean squared error. In the case of classification, we can use test accuracy. Right? And okay, and here we can use maximize or minimize. So maximize or minimize you can pass here. You can see objective type. So if you have classification problem, you can pass objective type equal to maximize, and if you use skin for regression, we can pass objective type equal to minimize. Then maximum jobs or maximum parallel jobs means maximum total number of training jobs to start the hyperparameter tuning job. And the default value is 1. And the maximum parallel jobs means maximum number of parallel training jobs to start. The default value is 1 here. So if we talk about here main, we can say argument in the hyperparameter tuning class, that is model object, then objective metric name, then hyperparameter ranges. Here we have just created, and then objective name. These are main here. Next we can call a fit method, but currently here I'm not going to run this because it will take more time, right? So you can run this by your own self after the class. Okay, and then after we can get the summary, right? Summary of the hyperparameter tuning process. So we can import from SageMaker Analytics, import hyperparameter tuning job analytics. So here we can get the summary. We can pass here argument like a session object and then tuner dot latest training job name, right, in the form of data frame. So here we will get the summary. Means here we have what will be the best score and what are the best hyperparameters, right? So these information we will get here in the summary. Then after, rest of the code will be same. So in SageMaker here we have a class hyperparameter tuner. We can see here we can tune this hyperparameter k. We have to use integer parameter. Range we can use this one. Sample size we can tune also. Okay, let's search here SageMaker KNN hyperparameter tuner. Training configure job. You can see here we can import integer parameter, categorical, continuous hyperparameter tuner. Okay, and this is a maxnet. So instead of maxnet, you can use the model like KNN or linear learner, right? That we have covered. So role, instance count, instance type, SageMaker session, job name, hyperparameter. Okay, you can see here best size column 100. And here we can pass hyperparameter ranges. You can see optimizer is a categorical. So here we can pass categories like SGD or Adam. And in the learning rate, which is also a hyperparameter, but here we have to pass float values. So we can use a continuous parameter. Number of epochs, here we have to pass integer values. We can use an integer parameter. You can see. And then for the objective metric name, we can use validation accuracy here. And here you can see hyperparameter tuning class, the estimator, objective metric name, hyperparameter ranges, metric definition. Okay, so in the further session, I'll try to show the complete example of this hyperparameter tuning. Okay, in the next session, we will cover dysentery and random forest, right? And after that, we will also see how to implement random forest and dysentery on AWS SageMaker, because in the AWS SageMaker there is no random forest algorithm. So we have to use this algorithm manually, right, in the AWS SageMaker. Right, so there are some inbuilt classes in the SageMaker, right, for which we can use any scikit-learn algorithm. Right. Okay, guys. So it is enough for today's session. Right. So let's wind up the session and let's meet in the next class. Thank you, guys.